Hi, how's everyone doing? Am I audible?
Fine, Farhan. Good afternoon.
Good afternoon, Ravinder. So, looks like we'll have to wait for a few minutes. We have only about 8 participants right now. I'm waiting for everyone to join basically because I just want to do a quick walkthrough of Slack and the channels and the resources and everything that has been shared there. So we're just waiting for all the participants to join because there is a little bit of a walkthrough that I want to do. Okay, so let's wait another minute and then we'll get started anyway. Yep. Okay, let's get started. So the first thing I want to do is just show you around how we have structured the conversations on Slack. So I'll share my screen. Right. I hope everyone can see my screen and can see the Slack window.
Yes, Farhan.
Cool, cool.
Yes,
Thank you so much. Cool. So if you remember, we like I had shared a link. I'm sure Kedar would have sent out that email, and it had a link to join Slack. Basically, that was sent out last week or maybe early this week, right? So and some of you were able to join Slack using that link, and when you joined using that link, you directly went to this private channel, right? This is for the India Standard Time cohort. This is our cohort, this cohort. So you were able to join here. So there were some I think 19-20 folks who were able to join with this link. But then I think that there was some sort of limit on how many people can join using that link, because I didn't have access to your emails, right? Because there were some concerns about privacy. So I just shared this link. But when we tried to like get everyone onboarded using the link, there were issues. There was some sort of a cap. So I sent out another link yesterday, which is an invite to the workspace. So instead of directly inviting you to the private channel, that just invites you to this workspace called No Chow, right? Now, because there are different channels, there is another one that you can see on my screen, which is for the PST cohort. But you wouldn't see this because it's a private channel, so only people who are added to this channel they get to see this. But when you are using a new link, you should get added to this general channel over here, right? And that is what has been happening. And what I have been doing is anyone who has been joining this channel using the new invite, I have been migrating them. I have been adding them to this private channel as well, right? So the how it's going to work now is that everyone will be there in general. I'll do another check again tomorrow perhaps. when everyone has joined. So because general is meant for general discussions, so there are people from other cohorts as well. You can see that the count here is 54. So you can just discuss anything related to reinforcement learning or anything in general. Just make sure that it's not related to Qualcomm or anything private or sensitive. You can do that here. But for this course, for our discussions, this is the private channel where we will have all those discussions. We will share the documents, references, anything pertaining to this course, right? And there are already a few items that I have shared here. So if you click on this pin icon over here, then then you see the list of items that I have shared over time in the last 2 days, and I have pinned them. So you can quickly reach to all these items, right? And so there is a list of other courses, which is just like a reference if you want to look up things. And then there's a list of actual references, which we'll be using some reading material. There are some of you said that they're getting introduced to Python for the first time, so there is one course which is like a very quick introduction to Python. If you know C, C++, Java, or MATLAB, and you want to get started with Python, so there's an introduction. There is a slightly more advanced course about the libraries we are using, which is NumPy and Pandas, and Matplotlib for plotting. So now these two links, this is something that you can cover in maybe 2 or 3 days very easily. So its name is Whirlwind Tour of Python, and it really goes very quickly through all the Python that is necessary for a course like this. And then there are some other references that we'll go through once we progress through the course, right? Then there is this pinned item, which is the link to our GitHub repository. If you go here, and I'll show you in a moment, but this, if you go to this repository, then there is a week by week structure, actually a session by session structure. And so everything is named starting with the week, like W1, W2, and then you have the session S1 or S2, or if it's an office hour, then it's OH, right? So all the starter code that we use in all these sessions, that is over here. And then other material that I share from time to time, I make it a point to pin that as well. So we discussed something called a bicycle model that was being used in the move function in our class when we are trying to drive the car. So here is sort of a derivation of that model, or how that model works. That is also pinned. uh, and this is a list that will keep updating. This is all the classroom material, so it will have link to the weekly slides if there are slides for a session. So slides will be here, the starter code, the recordings will be here. Like I mentioned yesterday, recordings take some time because I have to pull them out of Zoom, which takes some time because when a meeting ends, Zoom will generally process the video, and it takes at least a few hours to get it processed. Then I download it, then I upload it to YouTube because Zoom has limited space, so I have to like remove things from there. And then I share those links over here. So like this, the onboarding session, the recording is here. The session that we had yesterday, the recording is here. This is also pinned. This will of course keep getting updated as we go through the course. And then at the bottom you have the Zoom link in case you can't find it. It's right now there's only one link which we are using for Thursdays and Friday session. For Monday, because the timing is different, I will create a different link for Monday, or whenever we settle for our office hours. So that link will also go here. uh, so that's about it about the resources. And if like anyone is still not here, in general, if you haven't been able to basically access nochow, then let me know, and check your inbox. You should have gotten the new link. What I want everyone to do is take this poll. So we talked about it yesterday, but there has to be an office hour session which will be 60 minutes long. It's not strictly mandatory, like I mean, of course, there are times we're not able to attend, but what we want to do is sometimes we will have something that we did on Friday, right? We wrote a little bit of code but something was remaining, so we'll try to cover that on Mondays, and we will discuss the solution on Mondays. If we are working on a project, a take home project, we will discuss the solutions, the different approaches in Monday's session. So it's a good idea to attend that session as well. So what I want to know from all of you is which timings are suitable. Basically, the time slot is same, 4:30 to 5:30 p.m. India Standard Time. but then whether it's Monday, Tuesday, or Wednesday, that works best for you. So please, as soon as you get added to this channel, take this survey, and then let's decide which days work for us. Work for us, right? So that is everything about Slack. If there is any confusion, please let me know. I will very quickly uh, share. I will just show you how our repository is, or where the repository is. So the link I showed you a while back in Slack, right? That was the link to this repository, RL in action. Within this repository, there's a folder, and within that folder, you basically have the entire content, the starter code, and everything, right? So this is week one, session one, then week one, session two, because there's another cohort going on. So we already have access to these folders. But for any specific week, for example, for week one, session one, if we go inside here, uh, so basically all the important stuff is here. This is the code. This is the starter code that we were using yesterday, right? So you can pull this from GitHub, and these are the slides. So I'm generating slides from another Python notebook. So in case you want to look at what notebook looks like, you can pull it from here. But most of the time, if you just want to view the slides, right, so all you need to do is just just clone this repository. Basically, you don't need the entire repository. What we need is this file, which is an HTML file. It cannot render online. You need to pull it offline. And sometimes there will be resources folder which has images and stuff that show up in the slides. So we need these two, but the easiest way is to just grab the whole repository. And then if you like go to this file, if once you have cloned the repository and you open it, it will open in your browser. Right now you actually are looking at the HTML, but when you open it through the browser by downloading it, then obviously it will open up like a web page, something like this, and then you can like go through the slides if you want to look at something. uh, yep, I think that gives everyone an idea of how the resources are structured, right? Are there any questions? Anyone who still hasn't received the second email or is not able to join the workspace?
I received the second email, but I'm not able to join the workspace.
Okay,
I think so.
what we can do is when we end this session, so if you can hang on for a little while and just share your screen quickly, and perhaps I'll be able to help you
Sure,
join the workspace.
sure. Thank you.
Yeah, sure. Is there anyone else who is facing the same problem? Cool. Let me know if there is an issue, and I also shared my email, which I'm going to share in the chat again. So in case, yep. So when you use the second link, that is what I was just describing. When you use the second link, it actually adds you to the workspace, and you will only see one channel, which is the general channel. But don't worry about that, because I'm going to add everyone who has joined the general channel to the private channel as well. So that will happen right after the session. I added a few of you in the morning, those who had joined by that time, but I'll add everyone else. So if you are able to join the workspace, you're able to see the general channel, that's cool. There shouldn't be an issue.
I think it is other way for me. So yeah, I am in only the private channel, not the general.
Only the, oh yes, yes, they will, because if you use the first link, then
Yeah.
you would perhaps only have access to the private channel. So I'll add those
Okay.
names to the private channel as well.
Okay.
Thank Cool. So there's a little bit of presentation today, but we will interleave that with coding, right? So we were working on something. We were looking at a piece of code, and trying to solve a problem. So what usually happens is we will start with the starter code, we'll write some code, and in the next session, we'll probably move on to a different notebook. Why am I doing that? Because I just want to make sure that whatever we did in the previous session, we have the same code. Because when you're writing your own code, there might be a bug or something. So the ideal way to go about it is to grab the newest notebook. For example, for today's session, you can get the notebook from here. So I'm going to share this link. Yeah, so the link is in the chat and in Slack as well. So we just have to follow the same steps. Go to Google Colab, and then you go to File and Open Notebook, and then select the GitHub tab, and then paste this URL. Then you have to hit the search button, and then you would see a list of notebooks, right? So pick the one that first of all, let me try to show you, right? So it's actually reloading for me, but if you are doing it for the first time, right? So just make sure that the repository will of course be this repository, but the branch is the solutions branch, right? Why are we picking code from the solutions branch? Because it has some of the work that we did yesterday, so that would already be there. And then there's some additional code that we want to quickly explore. So make sure you are on the solutions branch, and then again pick the same notebook, car underscore track.ipynb. Okay, and please let me know if there are issues, but I'll get started. I'll execute the first cell, and then if when you're doing this, then it's a good idea to just go to file and do a again save a copy in drive, because that will persist your changes. It will create basically your changes will be saved to Google Drive. So I'm running the first cell and the second one as well. There are no changes here because we just froze the class. We created the car class and we experimented with it. Oh, yep, there's something I need to fix in my code. Yep. So what we need to do is, sorry, what we need to do is we need to change this URL over here. And again, the URL is in the chat. But if you are encountering that error, you just need to substitute this URL instead of the local path. Okay, is everyone able to run the code up till this point where you were, getting off the track around 73 steps?
Yes.
All right. So I will what I want to do is do a walkthrough of the solution that I attempted. But before that, I want to understand like who else gave it a try. I think Akshay tried around 500 steps or 700 steps, something like that. Was Is there anyone else who tried that approach that we discussed yesterday, and how far you were able to go? Okay, 636 steps. That's cool.
Yeah, I also got around that similar number 600 only.
600 plus.
Yeah.
Right. So if some like if anyone was not there on yesterday's call, then the approach was basically, take the 10 or so closest points to the car, try to fit a curve to it, find the slope of the curve at the point where the car is, and then try to change the steering angle to align better with that angle. So yeah, please post your the number of steps that you are able to get. And I am also going to show you. You already have the code. We'll talk about what these variables are, kp, kd, ki, but let's go line by line, right? So over here, this is nothing new. This was already happening earlier too when we were just using a trial and error approach. So reset the car, reset the class, set the speed to 20, set the time step to zero point 0.1. Uh, then there is all these variables. These are for debugging. So we can skip over these for the time being. But this is basically, again, the same thing what we were doing earlier, right? So there's a for loop. And now what is happening is I'm pulling out the nearest points, right? So we already created an API that gave you the nearest points. And if you go back and look at it, right? So this is the API, this is using the KD tree data structure, and it gives you 5 nearest points. Now we discussed some of these points will be behind the car, some of these will be ahead of the car. But for the time being, for a simple solution, that seems to work. So get the nearest points, and then there is this API in NumPy, Polyfit, which basically we will take the points. So what we are doing here when uh, nearest is like it's a variable with two different columns. It's a pandas data frame with two different columns. So it's a column named x and a column named y. The x is all the x coordinates, y has all the y coordinates. So and Polyfit expects you to pass a list of x coordinates and a list of y coordinates, and then the degree of the polynomial, right? So uh, what the solution or the algorithm that we discussed was that we can either fit a second order polynomial, or we can try to fit just a straight line, right? Both are approximations. Second order polynomial will be a better approximation. Of course, it has more flexibility, so it will fit along the points much better than a line. But to begin with, a line is simpler because if you fit a line, then the slope of the line is all you need. If you fit a second order polynomial, then there will be one additional line of code where you have to figure out the slope of the line.
So this is fitting a polynomial for y as a function of x, right?
Right, right.
Um, but what if it's, what if we're looking at a sort of verticalish section of the track where it's not really a function, right? So for each value of
Right.
x, there's two y values.
That will still work because it tries to find the best line. So the best line may not pass through all the
Mm,
points, uh, but
yeah,
there
got
are
it.
of course
Yeah,
issues. The actual what actually happens is when it's nearly vertical, then this method is a little unstable, right? So
correct.
what will happen is it will if you look at the slope of the line, that will change very frequently depending on which points you are fitting it to, and that is actually an issue that we will encounter, and that is why you will see that even this approach is not able to drive entirely around the track. It gets stuck somewhere, and if that has to be fixed, then obviously we need to figure out how to deal with vertical lines. But for the first quarter of the track where the track is not entirely vertical, you can grab the coefficient, and then of course the coefficient has in this case, because I'm fitting a line, there are two coefficients, one corresponding to the slope, which you can think of, if you think of the line equations and y is equal to mx plus c, then it is the m, and the other one is of course the bias or offset, which is in coefficient of 1. So coefficient of 0 over here is basically the tan of the angle, or what you call m in the equation of a line, right? So we just take tan inverse, so that we convert it back to radians, and then we convert it to degrees, because degree is a little easier to understand, and because internally we are also using degrees to store the heading, right? So current heading, of course, we can directly get that from the car class. Desired heading is nothing but the slope of the line that we just fitted, right? This is the approach we discussed, and then you take the error, right? So that error is going to be the difference. In this case, I'm subtracting current, I'm taking the difference current heading minus desired heading, and you can do it in the other the other way as well, desired minus current, but then you will have to take you will have to be careful about how you are using that error to adjust the steering angle, right? So just taking the difference, then when I did a little bit of debugging, I realized that there were cases where this was not between in the right range that we wanted. So you sort of, when you're thinking about uh, the difference, then that could be 0 to 360 degrees, it could be minus 180 to 180. uh, it makes a lot more sense to think about minus 180 to 180, because then you're thinking about steering going all the way left or all the way right. So there's a little bit of adjustment here to make sure that things lie in that range. This is something that you will figure out after debugging, right? But because I have gone through the entire debugging step, I have made these corrections. Then again, these lines, these are for debugging sake, we can skip over that. uh, but the thing that I wanted to show you is how we are updating. So this is what we discussed. You just find the error. This is how we must drive, because at every point we have some estimate of an error, and then we try to steer in proportion to that error, right? So just look at this equation, this part of the equation where we are finding the new steering angle. So what we are doing is we take the current steering angle, and then we subtract the error, right? So the error is right here, and we multiply the error by a small number. Kp is defined here as 0.005, right? So we multiply it by Kp, and then we subtract it. There are other terms, we will talk about that in a little bit, but we don't need this line right now, and we don't need the rest of the terms right now. This is the bare minimum you could do. This is, if you want to mimic human behavior, this is where you get started. So and it would make sense if you look at this equation, then you can see that the correction in the steering angle will be in the opposite direction of the error, right? So if you are to the left of the desired angle, then you should steer right. If you're to the right of it, then you should steer left. So depending on how you calculate, how you take the difference here, there could be a minus or a plus here. In this case, it's a minus. And then of course you're multiplying it by a small number, because you don't want to make a sudden change, right? And this is very basic. And then there is a little bit of sanity check to make sure that you're not trying to set a steering angle that just not possible, because the car has limitations. So that test is here, and you are then just setting the new steering angle, right? Again, this part, these two lines, they are part of the debugging code, they're not really necessary. And then we're calling car.move as we were doing earlier. So the only thing that has changed is that now at every time step, you are changing the steering angle, and you're changing that steering angle by mimicking the behavior, like how humans drive. How we drive is, if we know where at what angle we have to go, and if we know that our heading is different from that angle, then we make small changes to our current heading, so that over time we can align with that heading, right? So let's try to run this.
I had a question here. Why do
Yeah.
we have to multiply this KP into error? Why is this KP required?
Yeah, so KP is basically required because error could be quite large. So you want to only make small corrections. And how did I come to find this exact value 0.05? This was, so we know that we do want to multiply by a fraction. We don't want the arbitrarily large error to make sudden changes to this. And you can try that. You can just make KP1 and then see how just, you can log how much steering angle is changing at every step, and you'll see that there are sudden abrupt changes. Whenever the track changes, your steering will quickly try to follow that change, and that will be problematic because then it will just zigzag and go all over the place. So you do want to multiply with something. Yeah, so you do want to multiply by this thing, and I encourage everyone to like set it to 1 and remove the rest of the code. I will explain this in a little bit, but just when you are toying with this, then please
The
try to
error
remove.
came as an absolute error, right? And that's the amount of error correction you have to do. So you should KP not be 1? Why do you want to do
No.
it for small
Yeah,
corrections in each step?
so suppose you are going at 10 degrees but the desired heading is 15 degrees, right? So the error will simply be 5 degrees, right?
Mhm.
But do you really want to change the steering by 5 degrees?
See, the point is, again, how do you know the 0.005 is the right
Yeah,
step size,
that
right?
that is a separate question, but do we agree that trying to change the steering angle by 5 degrees is not going to work? That is not even how we drive, right? If I see lane lines ahead and if I see them turning left, if I'm going straight, I will gradually change the steering angle left, right?
So it depends, right? So if you're only looking at next point, yes, you need to do
Right,
this kind of thing.
right, right. Yeah.
If I'm looking at 10 points ahead and I am kind of having a tangent, a slope, then I'm okay, right?
No, so even in that case, because this steering angle is going to immediately get applied, right? The moment you call car.move, this steering angle will be used. So if you change it by 5 degrees, then during this 0.1 second time step, it will try to move in a direction, it will try to make a sudden move left, right? If we have computed the entire trajectory, but the slope you are looking at, that is, there is no common slope, right? The slope will change. The slope you looked at is the current slope where the car is. Of course, the track is going to bend left or right again, right? The 10 points will not have the same slope everywhere. This is the slope that we computed at the point where the car currently is, right? So we sort of want to align with that slope, and if the track is a smooth curve, then that slope will only change smoothly. So the hope is that if I'm going to align or try to align a little bit towards the current slope, then after one step I'll be a little bit closer. Then at that next step I will do the computation again. So I'll see if I'll try to fit the tangent again. I'll see if the slope is going in the same direction, maybe increasing. Then again I will increase the steering angle a little bit. If the slope has suddenly changed in the other direction, then the change will be in the other direction. And this is something which will become very evident if you set it to 1, set KP to 1, and then plot things. So I'll actually show you the plots, how they look like right now with KP set to 0.05. Now,
Mhm.
how do we get to that 0.05? That is a totally different discussion. Right here, it has been done through entirely like manual debugging, and you increase and decrease and you see how it is working. When you're building something, of course, that is not the proper way. So there are sort of algorithms or methods to do that. I'll come to that after we look at how it is working right now. But yeah,
Just a quick question. So what is that for loop? Can you just go up a little
yeah,
further?
yeah,
Yeah. So what is that for range for I in range 2000? What does 2000 mean there?
yeah. So if you look at how the code looked like previously, this was the code that we were dealing with yesterday, right? What happens is, what range does is it takes a number like 150 and it creates a list out of that, a list filled with integers. So if you just try to print, what you could do is just add a cell and try to print what this looks like. right? So just print, copy this thing.
I get that we do it 2000 times. So my question is, why are we taking 2000 as a number? Why not 3000 or 1000 is what I'm
So
trying.
the,
Sure. Yeah.
so ideally this should be based on how far you want to go along the track. Do you want to complete a single lap? uh, do we exactly know how many steps are required
Okay.
before
Okay.
going?
Okay. Got it.
So this
Got it.
is
Yeah.
rather arbitrary, but I just kept it to a large number, again
Okay.
by
Okay. Got it. Got
experimentation.
it.
So
Yeah.
sort of started at 500, I think, and it was moving perfectly till 500, then update to 1000 or something, then 2000.
Should we
Sure.
not do
Sure.
it as the size of the track? The size of the track is some 35,000, 32,000 or what?
No,
Points
you
track.
won't do it. You
Hmm.
won't do that because the size of the track doesn't really map to how much you move in one time step, right? So how much you move in one time step will depend on your speed and your orientation, and of course the length of the time step, right? So you could be covering many waypoints during that one time step. So it is
I
Just
think
possible.
one
when
time.
I think when since we started from x is equal to 0, y is equal to 0, I think after some this thing we can go till x is equal to 0, y is equal to 0, or
Yeah,
nearest point.
there are
Yeah.
different yeah. So if you want to complete exactly one loop, then obviously we will have to think about how to do that. We can obviously look at the nearest point and then decide. And if you want to be really accurate, then you will have to do a little bit of like write a little bit of extra code to make sure that you don't cross that point and start a new lap. But right now, for the sake of experimentation, this could be any large number. We were hitting 70 earlier. I wanted to see how far we can go. I tried 500, 1000, 2000. So it failed between 1500 and 2000. I think it was able to complete how many steps? Yeah, no, it failed between right after 1289 steps. But
So
yeah,
one more question, Farhan. So I
sure,
was
sure.
checking the error value, and the error value for the last 10 iterations is like 178 degree, 158 degree. It's
Yeah,
very high. And just
it's high.
before that, it was always less than
Yeah,
max was, I think I can see 10 degree or something like that. So, and
yeah.
I don't see the trajectory as such, which could cause that large an error. So why do you think that this error is?
I will give you I will give everyone a hint about that in a little bit, why that is happening. This is not a perfect code. This is definitely not going to drive you around the entire circuit. And if you think really hard about it, really how you would drive as a human being, then perhaps we will realize. But one good thing that is being done here is there's some debugging code uh, which you should look at its output. I'm going to show you a little bit of output. So when I run this code, I just wanted to show that when I run this code, I get around 1200 steps. But that's not really important. I think you can tweak things differently and perhaps get more or less steps.
I
Uh,
think,
so
Farhan, the reason for that is KP is constant there, right? KP is not depending on your new position and current position. That's why you are seeing uh, that suddenly it increases and we are not able to match that.
yeah,
KP, if it
I
changes with your
I think reason is we are fitting first order polynomial, right? I think that is the reason.
actually the reason is which someone was mentioning earlier, that when the line becomes vertical, uh, you have to think
Yeah,
about
exactly.
how np.polyfit behaves basically.
Right.
So
Right.
if it is like let's say 91 degree sorry 89 degrees and 91 degrees, then you have to look at what polyfit is returning. And because you can think, because we aren't really caring about the direction of the line, right? So is this line pointing upwards, or is it pointing down? Do you call it 81 degrees, or you take the
Yeah.
100-degree difference, right? That is basically the cause.
So
But
Farhan, I tried setting KP to 1 and KD to 0, and
yeah,
it actually went for more steps. It went
for,
for 1400 steps as opposed to 1280.
with kp set to 1.
Yeah. And KD set to
That is
0.
very cool. That is very cool. Let me try that. So let's set kp to 1 and set everything else to 0. Yep, it actually, yes. So there are two things. It's actually, yes, it does go till 1400 steps,
Okay.
which is cool. But yeah, generally you want to keep that multiplier there because you're never sure how much the angle is
Yeah,
going to
that I
change.
can understand. Yeah.
So the other thing is we already see some warnings here, right? It says Polyfit may be poorly conditioned. And if you really
That's probably
search
the
what this,
vertical.
yeah,
Yeah.
that is exactly the cause. So we are already getting that warning here. So you can, what I wanted to do is why I'm switching back is I wanted to explain a little bit more about why these choices, like what KD and KI stand for and why they are needed at all. Um, you can try zooming in on the trajectory. I'm logging the trajectory to a variable. You can just plot this. You can see that it is plotting this part of the trajectory that the car was able to cover. You can try further zooming in. So instead of plotting this entire track, just plot the last few. In Python, if you have like a list, right? So if you have this variable, which is a list, so you can print the last 100 or so. You can basically get the last few elements by using negative indices, right? So something like if I have a list L, then you can you can try to print the last few hundred indices. So instead of going all the way with the entire trajectory, just try to zoom in on this part, right? And what you will see is that this actually causes a loop. So the car starts turning so much. Yep. Is the audio okay?
Yeah. Yeah. We can hear you fine.
Cool, cool. So what I'm saying is that if you instead of plotting the entire trajectory, try plotting the last few points, and there's an easy way to do that
Farhan,
in Python. Yeah.
yeah, the audio is not okay. Actually, in between you go silent. Like in between your volume goes very down.
Okay, okay. So please point that out whenever that happens. I think there is a general, maybe I'm like speaking a little softer, but if the voice is fading or anything, please let me know. I see that message from you. So I'm trying to like keep the volume constant, but let me know if this happens again.
Okay.
Yeah.
So
Actually,
yeah,
I'm not facing that problem. So it may be very specific
yeah.
to
I
one of the
was
people.
actually
Yeah.
facing a similar problem with the other session where I think I was not able to hear the participants at all. I have raised a ticket with Zoom, but I haven't gotten a reply yet. But yeah, please let me know if there are any issues. So just what I was mentioning was that in Python you can print part of a list very easily using negative indexing. So try to use that, leaving that as an assignment, but try to print beyond, if it is going for 1200 steps or 1400 steps, just try to print the last 100, 200 steps and see what it looks like. Uh, the other thing which several of you already caught is that if you try to print the steering angle, right? So let me run this part again. So I'm just rerunning the code because I reset the values of KP and KD and KI and everything. So, and you can see that if you actually look at this graph, which, so this is when KP was set to when KP was set to 1, right? And you can see that the steering angle right here, it fluctuates between -20 and 20. And then over this entire region there's a lot of fluctuation, right? And this isn't a very realistic car, so you in one step you can have a steering angle of -20 degrees, in the next step you are free to set it to +20. So it's still a toy car, so that constraint isn't there. But if I try it again with the values that I was using for KP, which is 0.005. So you see that the steering angle makes small changes. It only goes up by 1 degree or -1 degree between those ranges. But then something weird happens near the end. So all of a sudden, this sort of shoots down all the way down. And if you try to debug that, so right here, we are just plotting the steering angle. But if you also plot the error, because error or not error, but actually the desired heading, right? So we want to see if the steering, because the steering angle is being computed from the desired heading. So is it the desired heading which is shooting all of a sudden? So you actually see that happen right here, that the desired heading which is in blue, that is shooting, and then the current heading, because it's being computed from the error, that is also trying to follow it, and then that is how things go haywire, uh, because of the issue that we discussed earlier, the track getting vertical and arctan or np.polyfit getting unstable. Um, but if you sort of zoom in and look at what is happening here, so the curve in orange, that looks pretty smooth, right? Wherever you see, it's a very smooth curve. The desired heading, it, it is a lot more zigzag, of course, because it just follows the track. The waypoints may not be perfectly following the track. So the waypoints may be, if you think of an imaginary line going through the track, then they could be to the left or right of that, which is a very realistic scenario. But the waypoints are zigzag, but this upper curve, which is the current heading, which comes from the steering, that is sort of able to follow this very smoothly all the way up to this point, right? And this is sort of how we behave, right, as human beings. So whenever there is a change, the desired heading is changing. For example, the desired heading at this point, between these 2 points over here, it had a spike. It suddenly went from, let's say, 10 degrees or something to probably 15 degrees, right, very quickly, because maybe there was a quick turn, or maybe the waypoints were not very well aligned, so it appeared like a very sharp turn. But our curve didn't see a similar spike. It tried to follow that change, but it did that more smoothly, right? And this is the behavior which you will expect from a good algorithm, from a good driver. You don't want to make sharp turns, which are both uncomfortable and unsafe. So it seems to be doing that. What you could do again is go back again, turn off KD and KI. I haven't explained them, but KI is already turned off, but you can also turn off KD and see if this improves or if it deteriorates. Don't only look at how many steps you are able to do, but also look at the debugging information. Like, how does this curve look like? Is this something that will be comfortable, which will be safe or not, right? So experiment with that. Uh, and then after that, there's a lot of additional debugging values which were basically used to find issues like this one that we saw where the steering angle was going haywire. Uh, so you could use that for your own debugging. But the point was that yesterday the goal we set up for ourselves was to go beyond the 73 steps, and we wanted to follow human behavior, which we seem to have done pretty well. I just want to explain what KD and KI are and why they might be needed. So the idea over here was to make corrections, right? So whenever you see that your heading and the desired heading are different, make a correction. And by multiplying it by KP, we generally try to make small corrections. In this case, even though you are free to make large spikes as well, but we try to, in a more realistic case, we would try to keep them small. So you multiply that by a small number. You have to manually adjust, experiment, and find out what that number should look like. And when you only implement this part where you are making changes in response to the error, you will notice that there is an oscillation. You will see an oscillation, perhaps that is present here. Maybe I can show you, right? So look at this part. If you were to zoom it out, then the desired heading is sort of constant, right? It may be 20 degrees or something, so it's constant in this segment. But if you look at how we are approaching it, so the current heading was, in the beginning, it was below the desired heading. Then it tries to slowly catch up with the desired heading, but then it actually overshoots. So if you think about, not in terms of this plot, but in terms of actually steering, then you were trying to follow a curve. You were probably to the right of the curve, but then you steered a little bit and you realized that you ended up actually oversteering and crossing that curve and going to the left of that curve, right? Left of the lane line, the desired heading. That is very prominent here. You will see it in other places as well, that there is some sort of an oscillation going on. So you overshoot, and obviously when you overshoot and you end up on the other side, in the very next step, you will find that now the error has changed signs. Now instead of being on the right, you are on the left, and again you want to align yourself back, and then you start steering back, which you see here. So the curve then the current heading starts decreasing and again coming back, and then it again seems to have overshot the value, right? Again, it starts to drop below the desired heading somewhere here, right? Um, this is also something that will happen when we are driving. So because everything is an estimation, so you estimate how much you want to steer, but then when you start steering, then obviously if you set your steering to a fixed angle like 1 degree or whatever, at some point you will oversteer, right? And how we approach that as human beings is that we turn the steering, but then we slowly let the steering come back to its original position, because we know that as we keep the steering turned, then we are slowly aligning with the curve that we want to follow. So over time we need to let the steering come back to the original position. Now different drivers will follow different patterns. If you are a very good driver, perhaps you will able to gauge everything very closely, and then you just make the corrections at the right time, and you just end up never overshooting. So you are just able to perfectly follow that curve. If you are a beginner, then perhaps you oversteer on one direction and then you make a correction, right? But you can implement a similar approach in terms of code as well, right? What is the idea here? The idea is that, okay, we are turning the steering in response to an error. That is okay, but the error, if we are doing it correctly, then the error is going down over different time steps, right? So perhaps we need to take that into account as well, and that is what is happening here. The second term is basically you're keeping track of how much error was there in the previous step, which is this variable, and how much error you calculated in this part of the loop, in this iteration of the loop, and you take their difference. That gives you an idea of how much error you were able to correct in just one step, right, in one time step. And then using that difference, you try to sort of compensate for oversteering. So you want to make sure that if this error is large, then the steering angle is reduced a little bit, and if this error is small, then the steering angle is not reduced by so much. So you still your steering angle is fine, and you don't want to make too much correction to it, right? So what we can do is we can perhaps do two different plots, one with KD turned off and one with KD turned on, and you will see the difference. The oscillation that you see here, it should be more pronounced when KD is turned off, right? Just how much of a difference it will make, how many steps you'll be able to go, that will depend on the exact value of KP and KD. But you will see, and this will be very very pronounced if KP is large enough and KD is 0 or KD is small, then you will see a lot of oscillation. And if it is the other way, if they are like in this range, then there isn't so much oscillation. And just how much oscillation you sort of can tolerate, that will depend on uh, the applications. In this case, perhaps this much oscillation is fine. I mean, actually depends on whether you're building a video game or a real thing, but that is the idea behind KD. Then there is a third term, which is KI, which we haven't really used here. But when you see that even if you correct for the oscillation, there is a tendency, like the steering will always have some small offset. So your car will never quite correctly align with the curve. It will have some small, maybe half a degree or something like that difference. And there is some underlying reason for that. There are errors that accumulate over time and which are not corrected by either the KP term or the KD term. And so what people usually do is they keep track of all these errors, the cumulative errors, and then they make an additional change to account for those errors, whatever small errors have accumulated over time, right? How did I figure this out? So this is nothing that we invented. This is a well-known algorithm which is called PID control. So uh, uh, the PID basically is an abbreviation for proportional, integral, and derivative. So this term is called the proportional error, of course, because this is in proportion to the error. This is the derivative, because this is the the rate of change of the error, because the time step is fixed. So this is sort of your rate of change. So this is the D in PID, and this part is the I in PID. Uh, PID is used in a lot of circumstances. It is used in actual cars as well. There are lots of other examples. Anytime there is an actuator that you want to control smoothly and you want to get very precise positioning, PID is a good algorithm. The real issue with PID is how do you get KP, KD, and KI right. So for things, so another application outside of self-driving cars is, for example, in the old style hard drives, right, where you had platters and reading heads. So the reading head is basically some kind of an electromechanical device that you want to precisely align to a point, right? You can, it's pretty much like driving. But whenever you apply a voltage or current, try to move it, there will be small changes, so it will never perfectly align. So the idea is same, that first of all, how much voltage you want to apply to it, that sort of will come from here. So where do you want to move it, how large that delta is, that will come from here. But then you will see some oscillations, and to correct for those oscillations, to make sure that those oscillations are not very large and then they die out very quickly, so you have to introduce a second term, which is this second term here, the derivative term. But you will still see that if it doesn't align perfectly, and there is a need for the integral term. So that is the PID algorithm. The point here was, we started by looking at this problem, which was a planning problem, right? And we saw why this is a planning problem, because you have to look in the future. You have to you have to think about how, what you want to do in the next few time steps. And then from there, you sort of figure out what you want to do at the current time step. And then there's the control part, which is actually figuring out, okay, if I want to steer the car to the left a little bit, just how much that little bit should be. That is this part of the algorithm, right, where you're multiplying the error by KP and then trying to adjust things. So it was a planning and control problem. We used a well-known algorithm that has been proven to work in a situation like this. But what we got started with was that we wanted to learn this behavior. We don't really want to follow exactly this approach. What we want is, what if I drive the vehicle around the track a few hundred times, a few thousand times, maybe millions of times, but I collect a lot of data on steering angles. Can I learn from that alone? Why would I want to do that at all? I'm going to cover that a little bit, but just wanted to highlight that we aren't exactly learning much here. There is a fixed known formula. We do want to figure out these coefficients from trial and error, but there is no learning algorithm going on. But during the course, the next few sessions, next few weeks, we are going to focus on solving such problems involving planning and control. But we want to be using some sort of a learning methodology. We don't want to, and there will be occasions where we already know a solution using an existing algorithm, but we will forget about it for the time being and focus on a learning approach. Why we will do that, I'll show you through the slides in a second. But at this time, if there are any questions, please ask them now, because we're sort of going to then move away from this problem. This is a little bit too complex to get started with in the beginning of the course. So we'll keep coming back to it, but we won't use it as a running example for the next few weeks. And I would request everyone to like take the code and play with it. Like someone figured out that if you just turn off KD and make KP1, it still seems to work. It actually seems to outperform. So what other combinations are there, and how far can you go? And probably if you want to take a better shot, then try to fix this problem. You will see you can plot what values, the basically what coefficients you are getting over here. So see how, are they changing smoothly? Is there an abrupt change? And if there is an abrupt change, then what is the underlying issue and how that can be fixed? The hint is that somehow we need to keep track of the direction in which we want to move, and that direction might become ambiguous in a lot of cases. For example, when it's vertical, So how do you keep track of that? How do you know that these are the points that are ahead of the car, and these are the points that are behind them? And so whenever you fit a line or curve and take a tangent, so you also have to figure out that direction of the tangent. So you always take the right angle. So give it a try, but we will sort of move away from this example to something new. I'm going to talk about that in a little bit. Uh, just wanted to run everyone through the course syllabus. So we are right now we are almost here, right? So we started thinking about what reinforcement learning is, what sort of problem it solves, and to understand that, we came up with this problem of trying to drive a car. We saw how this is a planning and control problem. Now we'll move on to another planning and control problem, because we have some understanding of what planning and control is, what it entails. But we want to make that problem a little bit simpler. In what terms? So we want to make it discrete, basically. So instead of having a situation like a car where you can turn the steering angle, you can turn the steering between -25 and 25. You can set it to any arbitrary position, which is like assigning any real value to the steering angle and to speed. We will focus on a problem where these decisions they are discrete, basically. Like, so where instead of thinking of a steering angle, think of a joystick. So you can either take the joystick to the right or to the left, and there are no intermediate positions or up and down. So that makes it a little simpler to reason about things and think of the planning and control part. And then once we have explored algorithms, when we really understand how to learn this behavior on a discrete system, we are going to come back to problems like the car driving situation, where things are continuous. So this is where we are. We are going to get started with Foolsball today, the other environment. Just wanted to give a quick rundown of what we did yesterday and today. So we what we were discussing earlier on the first day was that we are able to learn perception and reasoning with neural networks, for example, or any other kinds of supervised learning. We want to learn. We want to be able to learn planning and control as well. And the question which is still open is, can we do that with supervised learning? We will see that the reason we need reinforcement learning is that planning and control are a little bit different from supervised learnings. Not trying to answer that right now, but yeah, this is what we are after. And to understand what planning and control looks like, we were dealing with this example, trying to drive a car. Okay. Was it a planning and control problem? We have discussed that. And how did we solve it? We just tried to mimic the human behavior. So this is code snippets from the code that you just saw. How is it? I hope everyone understand how we are mimicking human behavior. So this is essentially that part where whenever you see that there is some deviation, you want to make a change which is small but opposite to that deviation, right? And then we went one step ahead and we thought about how do humans control the steering angle once you start to approach the desired angle. So we made some more changes, and that seems to help. And everyone has seen this plot, so I'll skip over this. Right. The thing I really want to talk about is these issues. So were we able to steer correctly? Yes, there was some underlying issue with the angle calculation, but if you figure that out, then this seems like a promising solution. There is no issue with KP, KI, and other stuff. The issue seems to be with calculating the angle correctly. But the other big challenge was how do you tweak KP and KD? How do you get the right values? We didn't really discuss that. We didn't really experiment with that a lot during the sessions. I did it offline, but it seems to be trial and error seems to be the way. We didn't really try to control the speed. If someone wants to play with that, you can build a similar controller with another set of KP, KI, KD for speed as well, and then you can try to control both as you go around the track, and perhaps that will give us better results. But perhaps the biggest issue was that we simplified so many things, right? So there were so many constraints that were overlooked. I mentioned one, which was that you cannot really jump around in terms of steering angle, because steering on most vehicles is a very smooth thing. So you can only move the steering by a certain amount during one time step, and you can also not jump around, have large jumps from one direction to another direction. Of course, we haven't really introduced a very robust or very sophisticated physics model, so there will be lots of other issues. We have approximated the whole car by a bicycle, which is which could be okay if the time steps are very small. But even in that bicycle model, there are additional things that could be accounted for. There could be friction, skidding, different other elements present in the environment, their effect. So all of that has to be perfectly modeled, and then your algorithm will be able to uh, work correctly, right? And that is why if you apply a PID controller to something like a hard drive, it is very easy to get things right, because you can tweak things, you can control the environment, you know which environmental variables are going to change. But if you want to apply to a real self-driving car, or some sort of a robotic arm that you have to move around, then it tends to be a lot more complex, right? And that is what we want to learn. So simple problems are already solved. You can implement a PID controller, it already is implemented, it works pretty well. But if you want to generalize, if you want to build something more robust, then you have to think about how to learn that behavior, because if you're able to learn the behavior, then hopefully it will generalize to a lot more situations than a hard-coded algorithm can. So, and of course, the environment was also static. There were no other obstacles, no humans, nothing else moving in the environment. So we were definitely not, the planning part didn't include any of this. And another very real world thing, we had access to all the data. We weren't really using all the data. We were just looking at maybe 5 or 10 points around the car. But if we wanted some sort of planning where we want to look at the entire data and then perhaps pre-process it and add some more information to our decision making, we could have looked at the entire track. That option was there. uh, all of this is generally not available when you're dealing with a more realistic problem. Uh, and again, a very important thing is that this entire setup was reproducible. If I was trying to build the same PID algorithm, but for a real car or even a toy RC car, perhaps, it would be a lot more difficult because, for example, when I'm trying to tweak KP, KI, and KD, I cannot reproduce the same behavior again. There will always be small changes, and those small changes amplify. So it's very difficult to be able to reproduce the uh, exact same coordinates or exact same trajectory, make the car follow the same trajectory every time. And that means that it's a new experiment every time, and that just makes it harder to tweak things manually. uh, can we learn to do that? We will find out through the remainder of the course. Why learn? For all the reasons that we saw earlier. So the moment you start thinking about more realistic problems, you realize that it is going to be very difficult, if not possible, to have a hard-coded solution. And hard-coded solutions exist. They are used in the industry as well, but those are very specific problems in very restricted environments. If you want to build things, algorithmic agent or physical agents that are able to deal with more flexible situations, then you need some sort of intelligence, some sort of learning behavior. Can we use supervised learning? Okay, that is a question that we will keep coming back to for the next 2 weeks or so. But can we use supervised learning or not? And I want everyone to sort of think about it from whatever information we know right now. And we know about supervised learning, right? So can we solve this with a supervised learning approach?
The error that we are getting, right, we can feed that error as a reward, and that can drive the next step. So we are actually blindly taking decisions without using the error. Right? So I mean, there
So
should be, yeah.
So we were using the error, right, in the PID controller.
But it's again KP, KD, and KI are not learned parameters.
Okay.
They're not
Right.
fixed.
Where would we get the ground truth for training the
Yeah.
supervised learning?
Yeah. So that is the first question, I think, which is difficult to get. So what do we need in terms of data? Perhaps if the situation is like this, exactly this environment. So I think if you think about ground truth, then perhaps waypoints and the steering angle. Of course, some human actor, someone has to drive around the track a few times, and with different starting positions, different starting steering angles, and collect that data. Perhaps that could be fit to an algorithm as a pair. So if the x and y, but if the next 5 points are these points, then then the steering angle should be this much, and then we can hope that the algorithm learns to interpolate between these points. So if it encounters a trajectory which is none of the trajectories that it has followed so far, it is still able to generalize well enough. Seems possible. um, so of course, what is our data and label going to be? I think it will be trajectory points and steering angles. And what will be the cost function for a problem like this? Because supervised learning will require you to minimize some sort of a cost function. So what would that be? Is this something is this something we can think of naturally as a cost function?
It would be the deviation from the ground truth, right?
So yeah, if you want to follow that approach, then it's actually called cross track error, I think. So the idea is how much you are deviating from the track. You measure that in terms of angle or in terms of distance, and maybe square it and sum it up, and you can take that, like sum that error at individual points, or take like use a window and take the average error over that window.
So
But
here there are many configurable parameters, right? There is the speed, then there is this time instant, and the length of the car, and such things.
Right.
And then the KP, KD, and KI can vary for different speeds that we are running at. And the five that we used, the nearest points, 5 nearest points that we used for interpolation or some kind of a,
right.
getting the trajectory, that also can change. So several hyperparameters here, isn't it?
Right. So if you think about all the possibilities, it's just too much to control with a single algorithm. But
Yeah. And
hopefully, perhaps if you have like a million data points for this track, then perhaps you can learn this. There is a paper out there from NVIDIA, which I'll share, I think, after the session, where they take a similar approach. They actually use supervised learning and pretty much similar to what we were discussing, and they're able to figure out the right steering angle by just from going through a lot of data.
Mhm. And do you think you used a single order polynomial, but what about multiple orders like 2, 3, 4?
Yeah, so there are lots of things. So you definitely want to do a single order. I mean, second order gives you more flexibility. All of us know, because it can take a shape which is closer to any sort of curve. But do we want to take a third order, fourth order polynomial or not? That is a very interesting question, and that is actually related to something we do in supervised learning, right? So in supervised learning, whenever we want to fit a curve or approximate something, basically learn what that curve is going to look like, we are always wary of overfitting, right?
Mm.
And if you pick a polynomial which has a higher degree, it has a tendency to overfit, and that is natural, because the higher the order of the polynomial is, the more it can wiggle around. So if you take a fourth order polynomial, it can go up and down quickly. It can assume all sorts of shapes, whereas a second order polynomial, that can only bend in a particular direction, right? So if it has a positive coefficient for the x squared norm, it can only bend upwards. If it has a negative coefficient, then it can only bend downwards. So if you introduce fourth and fifth order, the issue really what really happens is that then you do have a lot of flexibility. So perhaps your polynomial will in certain cases fit very closely to all the points. You get a very good approximation, but then it also tends to jump around a lot, right? And you don't want that. You don't want a polynomial which, if you think of 5 different points, then you don't want something that, although it goes through all 5 points, because it's very flexible, there is a lot of zigzag or there's a lot of oscillation between those points. You want something which maybe does not go through all 5 points, but it gets as close to all 5 points as possible, and then it's very smooth, so you can actually follow that curve. So typically you would use second order or a third order polynomial, and this is exactly what is done. So because and there are measures, there are metrics to sort of compare like second order or a third order polynomial and see how well those polynomials will be as a trajectory. Because then not there are a few things. There is of course the question of whether following that trajectory is feasible or not. If the order is very high, if the degree is very high, then obviously, like I said, there could be a lot of twists and turns, and it may not be possible for a vehicle with all the physical constraints to follow that. But if you also move beyond that, if it's an actual vehicle, then you also have to think about the comfort levels. So even if you can follow it, do you want to like throw around the passengers because you're turning very quickly, right? So all of that, all of those constraints also have to be figured out. So generally you will keep the degree low, 2 or 3, something like that. Right. Going back to learning, if we are able to learn the behavior from lots of trajectories and driving angles, how do you think we will be able to measure the quality of learning? When will you say that, okay, the car has perhaps learned to drive around this track?
Yeah, as you told, take the square of the deviation and sum it up, and yeah, and see if it is very less, right?
Yeah, again, the same things come into play. So of course you want to minimize because that is part of your cost function or objective. So obviously you want to minimize the deviation at every point. That is one measure. You can also include other things like how much oscillation there is. That depends on because that depends on the use case. So the metric will be maybe different from the cost function.
And also I think after learning how fast we can reach the destination, that is also another thing, right?
Right, correct, absolutely. So you want to minimize the time it takes you, right? And especially if you want to learn the speed as well, then you want to minimize the time. So introduce something into your cost function and in your metric that sort of accounts for that.
Also the smoothness of the heading curve.
Right.
Yeah.
You want to regularize that as well, yes. So perhaps that will be part of the cost function as some sort of regularizer. So what we want to do now is move a little bit towards formalizing this problem. Like if we are talking about planning and control, can we solve all planning and control problems can we learn all planning and control problems, or which sort of problems we can learn? So what we're going to do is we will pick up an even simpler problem with fewer controls and discrete controls, right? Why? Because we want to be able to visualize and debug everything. You can see that even with that simple setup, it is non-trivial to be able to figure out what is going wrong. So when you're learning things, there's additional complexity. You want to keep the system simple. Before I move on to how we are going to do that, there's a simple quiz for everyone. So there's a question on your screen. What do you guys do when your machine learning model is training?
Check whether your cost function or loss function is right, or you can do a better one.
Okay, so maybe keep tabs on your TensorFlow dashboard. Okay.
Yeah.
This is a fun question, like give it a try. Who else does what? Watch a movie. Okay, fair enough. You can, I mean, yeah. If the model is training for 2 hours, then it's the best time to watch a movie. Yeah, there are lots of things. Yeah,
basically, you need to keep checking whether it's converging, right? So generally, when we are training, we should keep checking whether the thing is converging. Otherwise, we just have to stop it and go back and probably.
Yeah, Yeah. So obviously you should care about that and keep track of things. But there are lots of excuses as well. Like my model is training, I'm free to do X. Cool. I see a lot of serious answers. Okay. So what we're going to do is, yes. So we are going to build an environment, by which I mean we are going to build a class, which will be another planning and control problem. We are going to call it Foolsball. It is a toy version of soccer or football, or you can even think of it as a miniature version of foosball, right? The thing that you like have your in cafeterias or gaming areas. So it is a very small environment. You might think it's a very toy problem. Why are we even bothering solving it? But the thing is that we want to learn a lot of things about how planning and control problems can be learned, basically. And that will involve looking at every bit of information and debugging it, and then understanding how it works, why it doesn't work, how to fix it. And for those purposes, this is a very good problem. We'll see that. But this is what we are going to use. So it's a simple problem. Over time, we will add complexity to it. We'll start with a simple definition like we did with the car class, but we can add complexity. You can, in fact, make it something like which will behave like this. It won't exactly look like this soccer field. This snapshot is from a reinforcement learning platform or framework that Google has built, where you can play a game of football and you can control the players algorithmically. And obviously, the intention is to test out different reinforcement learning algorithms, see how well they can learn to play the game, the different rules, and the behaviors. uh, there are different ways you can interact with this environment. You can either just look at the screen like humans do and then think about which player should make which move, which action, or there is also access to the ground uh, truth, sort of. So you can ask the rendering engine, the game engine, to tell you which players are where and where the ball is and where the goals are in terms of their coordinates, and based on those coordinates try to build an algorithm, right? So the at the outset, the environment we are building is very simplistic, but over time, if you add keeping complexity, you make it more complex in terms of size, in terms of the rules, in terms of the possible behaviors, then you can build something which is uh, very much complex like this one, and not just complex but more realistic. um, what are we going to do today? We're going to start to build this environment. We have obviously like about 40 minutes or so left, so we are going to attempt only to build a part of that environment. We'll continue in the next session on Monday from there, but we are at least going to look like the specification for that environment and why the specifications look like that. And then once we have the environment ready, we will start interacting with the environment to understand, uh, like we did with the car environment. Initially we try to drive it with different steering angles and different time steps, uh, and then use that interaction and the environment setting, the whole setup of this environment, to understand the terminology that is generally used in reinforcement learning, because we want to be able to go back to different resources, books, and otherwise, and we want to understand what those books are saying. So we will build up our terminology using this example. So to get started, here is the link to the other notebook. Now this is again in the same folder on the GitHub repository. I'm sharing this in the chat box as well. This is the notebook that we need for the rest of today's session. Goes to Slack as well. Right. So again, the steps are same. You have to go to Google Colab, and then you basically you clone this notebook from GitHub, and make sure you go to file and then select save a copy in drive. This will make sure, because this is a lengthy task, so you will have to leave it today after some time and then come back to it on Monday. Make sure you go to file and then save a copy in drive, so you have all the changes saved locally. So get this notebook, and then I'll talk a little bit about what the environment is, and then we'll spend some time to start implementing that environment. Okay, in the meanwhile, yep, I'm all set. I already have the notebook open, but just grab that URL and make sure you, because there will be multiple copies of the same with the same file name. So make sure you get the one which is from W1S2, which is week 1 session 2, which is where we are right now. And it has to come from the master branch. There are two branches on GitHub. One is the master branch, one is the solution branch. The master branch has the starter code for every session. The solution branch gets the full solution. This generally happens after the session is over. So idea is not to hide the solutions. The idea is that everyone gets a chance to write their own code and practice a little bit, and then obviously share the solutions, so you have something uh, as a baseline or as a reference. Okay, I hope everyone has been able to like get this off GitHub, and you're looking at this part where we are describing what the environment is, right? So it's a very small text environment, which means the whole environment will be represented as a sequence of characters, or you can say as a sequence of strings, right? This why did we make this choice? Because this really makes it easy to print the environment. Anytime we want to debug the environment, we can just use the print function to print the entire football, the football field and the players and everything, right? If you look at existing frameworks like OpenAI Gym, they also have some what they call toy text problems, because these are the easiest one. They don't require you to render anything. You don't require a GPU. You can even work with uh, work inside something like Google Colab, which runs in the cloud. It doesn't really have access to a screen where it can render things, so it makes it really easy to display the environment. What else we need to know about it? It's a very simple setup. The entire field is like a 5x4, so there are 5 rows and 4 columns, and that sort of makes up the entire playing area or arena or whatever you call it. Uh, there is a player. You don't really see the player. It's really difficult to have the player and the ball both in one cell, like display them both. So we just see the ball wherever it is on the screen, wherever it is on the field. But the ball is, or the player is always, when the game starts, it is always in the top left corner, right? Uh, I'll show you exactly how the layout looks like. But after that, you what the controllable part is that basically you can move around the ball or the player in 4 different directions. So you can go up or north, or you can go down, or we're calling it south, likewise left and right. And this can be done using an API, which we are going to build. Then there are opponents, representation of opponents on the field, and you will see this green jersey, uh, which wherever an opponent is present. And all these opponents are static, and that is why uh, it's a very foolish approximation of a real world scenario. But we want to keep things simple. So right now, for the next few weeks, these opponents are going to be static. So wherever they are at the beginning of the field, their positions are fixed. There is a goal post which happens to be at the right corner, right bottom right. And obviously, because it's a goal of, it's like a football game, so the goal is to take the ball to the goal post, score a goal, and stay clear of the opponents or the defenders, right? So that is what we are describing here. So we want to reach the goal post. So if you look at this piece of code over here. So initially the ball is here. You want to take a sequence of steps. You want to bring the ball over here. So the goal and the ball are in the same position. And at no point you want to step into one of these defenders, right? Uh, so if the primary goal is just scoring a goal, there could be secondary goals we'll talk about later on. But like with driving, we want to do it in an efficient manner. We don't just want to wander with the ball here and there. We don't want to do things like trying to take the ball outside of the field. So we want to penalize those actions. We want to do it in an efficient way, and we will define exactly what we mean by efficient later on. What are the games of the rule? So like I said, the ball can be moved in only 4 directions. The other interesting part is if you think of it as a video game, so how much reward or how many points you get. So there is -1 point every time you move the ball to a vacant position. These are all vacant positions, right? So if you move the ball from here to over here, then you get a reward of -1, which is basically saying that you are penalizing the player for moving the ball there, but it's a small penalty. If you happen to move the ball into one of the defenders, the green jerseys, then there's a larger penalty of -5 points, right? Similarly, if you want to move the ball outside of the field, right? If you want to go up from here or if you want to go left from here, uh, both of which positions are blocked because it's outside the field, then again you are penalized with -1. But if you eventually are able to move the ball into the goal post, which is like the goal of this problem, then you get a reward of +5 points, right? So we call this thing reward structure. I don't want to give it a name right now, but we're just calling it the rules of the game for the time being. Does this make sense to everyone?
One question. So anyway, he cannot directly reach from the source to the destination, right? He cannot do one hop and get a +5. Is that possible?
No, you cannot. No, that's not possible. Obviously, you
Maybe
have
he has to go to empty points where he gets keep getting -1, -1, -1. He could get
Right.
-100 before he actually goes to the goal.
Right. So what? Yeah. No, that's right. Absolutely right. We that can happen. The whole point of learning will be to not let that happen. We don't want the goal should be scored, and it should be scored through the most optimal path, the shortest path.
So now, one doubt I have here is, what is the learning here, right? See, I can achieve this through an all combin or shortest path algorithm,
Right.
Dijkstra's or whatever.
Right. So again, going back to the same example with the car stuff. So because right now the setup is so simple, you can just apply Dijkstra's algorithm or dynamic programming or another approach, and you can just find the shortest path, because this is nothing but in the current avatar, this is nothing but a shortest path problem. We will not use those approaches because we know that over time we are going to evolve this into a problem where these solutions will not work. And we will actually see, when we try to attempt to solve this, we will actually attempt one solution using dynamic programming. Uh, if you just want to like check if it can be solved with the shortest path algorithm, of course it can be. You can just do it in perhaps polynomial time as well. But why we are not doing it is pretty pointless, because then we will change the environment, we'll make things non-static, we will introduce probabilistic actions, and then it will become difficult, and then it will become impossible to solve it using the traditional approaches. That is the whole point of being able to learn things. As long as you can efficiently solve something using an existing algorithm, there is no reason to even try to learn.
So when we learn here, right? So what is the learning here, right? So so I changed the green jerseys, location of the green jerseys, and still he will be able to reach the goal within whatever order of 1 or order of 2, order of n, right? Is that the plan? Is that how it is going to be?
So right now with the current setup, the green jerseys will be in place. They will exactly where they are. The goal of the learning is to find a path where that doesn't that just stays clear of the defenders, and you are able to score a goal. And of course that path should be the most efficient, so there are no loops, and you take the most direct, most simple, shortest path from the starting point to the ending point. This is the learning goal for the foreseeable future, because we just want to explore the learning approaches. And then when we start adding complexity, then we will start even moving around the players, starting from different initial positions, introducing actions which are not perfect. For example, you are trying to move the ball to the right cell, but maybe you slip a little and the ball actually moves down, it goes south. So we'll introduce all of that, but for the time being, what exactly we want to learn? We want to learn the sequence of actions that will take you from this top left corner to the bottom right corner without going into any of these cells, the green jerseys.
Quick doubt. So what is this unmarked position? Everything is an unmarked position except green jersey's position, right? Did I
Right.
get it
So
wrong?
no, no, this is, you are absolutely right. So look at the first row, right? This makes up the first row, and this is represented as 4 different strings. So the first
Mhm.
position is obviously the player. The second position is unmarked, it's empty. The third position is taken up by a defender, it's marked. The fourth one is empty. And then you have a bunch of empty unmarked positions over here, and in this column, and in this column, and over here. And obviously the other positions are they are being uh, they have a defender in them. So the unmarked ones are basically these are spaces, right? Empty strings sort of.
Yeah. So meaning uh, I can only get a negative point wherever I go, right? So
Yes.
okay, can I jump 2 positions in one shot? No, is it possible?
No, that is not possible, because the rules say that you
Okay.
can only go northeast of the south, so it's only
Right,
one step at a time.
right. So see, even I take the best possible route. I go south 2.3 points, minus 3, 4, 5, 6, 7, and then I go to plus 5. So I will still end up with minus 2, right? So there's no way I can get to the goalpost with a positive number. Am I right?
Yeah, no, you are absolutely right, and there is a reason. So right now, it is arbitrary, but it's not totally arbitrary. The reason that you are still being penalized for every step is that we want to find out uh, a path which is the shortest one. So if you make this reward, for example, 0, or if you make it positive because you want to sort of reward the player for being able to make one correct move, that also incentivizes all sort of behavior where the player can just loop around. It can go right left again again, and you don't want to do that. We don't understand that yet, like how the reward structure is going to how that is going to affect the behavior. So right now you can just consider it as arbitrary. We are not even going to stuck with stick to this reward behavior for the for like the entirety of the
Okay.
4 weeks or so. So we'll keep
Okay.
changing this. For right now, just the explanation is there. -1 is there because we want to penalize it, but we'll figure out how exactly to set the reward structure.
Sure. Okay.
Cool. Any other questions? And I hope everyone is able to understand these rules. And then obviously this is the first cell that all of us have to execute, because this is also where we are defining variables. So there's nothing fancy here. We are just using certain characters which happen to render like certain things. So these are all strings. This is one string which with a Unicode character that renders as a football. Then you have another string that renders as a t-shirt, and then you have one that renders as a goalpost. So these are just 3 normal Python variables. There's nothing really extraordinary about them. Then we have a fourth variable, which is a list of lists, right? So it is a 2-dimensional list. So there are individual lists like this one that represent a row, right? So you have first row, second row, third, fourth, and fifth row, and then the outer list is sort of storing those 5 different lists. If I hope this is making sense to everyone. If you are new to Python for the first time, then probably you need to experiment a little bit with just numbers or other characters instead of Unicode. That will probably make more sense. But there really is no magic, nothing new going on here. We have used these characters because it just looks good to the eyes when we are printing things. It will look a lot better if you have an actual football versus I could have just gone with a number like 0 and 1 or x. That would be a little hard to visually grasp. So if there is any confusion, let me know. But if you run this cell, you are basically defining these variables. So agent is a string that represents this football, opponent is another string, goal is another string.
Yeah, just
What do we?
sorry, it's taking us one more minute to maybe think ahead to see if this is in the same path of the expected. So what I would do with this is that I'll just go find all kinds of paths and apply the reward or penalties, and then whichever path will have the lowest score, we will end up picking that one. That would be
Right.
like a
That is like the simplest brute force approach. So just enumerate all the possible paths. Some of them won't even take you to the goal state. Some of them will do, and then you can just calculate the sum of the reward that you get. And the way the rewards are structured, they ensure that if you take the shortest path, you get the highest reward. Now, that reward could still be negative, but it will still be highest. So you can just pick the highest reward.
yeah,
Uh,
and it's like maybe simplify that, saying that yeah, as long as the moment you find a path that has a better, better reward or a lower penalty, you just
right,
they just kick out the guys who are already hit as a
right,
match.
right.
That,
I think that is the approach we use in the Dijkstra's algorithm, right? Where you the relaxation steps. So whenever you find a shorter path.
yeah. Okay. All right. So we are still
No,
not going to be in that.
yeah, we still don't want to use that for obvious reasons, like
All right. Yeah.
because this is going to change. Uh, yes. So what do we want to do? We want to build a class that takes these variables. So right now these are strings and individual variables. We want to store all that information in one place. So it represents an entire game of football. Uh, and if you look at what we really want to do is we want to have certain APIs. Uh, why these APIs are why are we picking on certain names? Like there will be a step API, there will be a reset API. This is because in future when we are going to use something like an OpenAI gym, then we will be a lot more comfortable because the gym environments all have the same APIs. It turns out that many of the reinforcement learning problems they can be simulated by using these APIs. So we are going to take a look at those APIs. So we want to build a class. Let's call it Foolsball, and it will obviously have an initializer, which is like a constructor. This is where you want to initialize the variables. But in terms of other APIs, the public facing APIs, uh, there is something called set rewards, which basically set the reward structure that we talked about, different points that you get for different types of actions. We want a step API that is pretty much like the car case, right? Where we had a move API. So there's this a step API that lets you move up, down, left or right. There is obviously a reset API because you want to be able to restart the game all over again. And there is a render API that lets you basically look at something which is visually interpretable, right? So whatever the state of the game is, you want to take a snapshot of that and print it. This is what we want to implement. Now, obviously, because when you actually try to implement this, there will be some helper functions. So we will go in a very slow step-by-step function. There's a lot of sort of hand holding right here because I tell you what to do and how to do it. We are going to slowly ease that off. But right now, because we are just getting introduced, it's a good idea to stick to a common coding pattern and like everyone writing almost the same code. So we'll keep it narrow. We will add constraints. You can say that basically we have a lot of starter code and we are only making small changes. But we want to. This is what we want to do. This is sort of what to do, and to reach there we will do that incrementally. So if you look here in the left pane, there are about 12 steps that we have to implement. Now today we will at most be able to do one step, right? But eventually we have to go through all those 10 or 11 steps. There are 11 steps. This numbering is a little bit off. But right, so the step one, if you look at step two, basically, because the step one was specify the APIs, which we have done, which I have tried to explain. Look at step two, and there is already some code added to it. So there is this method, which you're calling toState. It has underscores in the beginning and the end, just to highlight the fact that this is not supposed to be used from outside the game. Sorry. So that is more of a convention. But there's this function toState, which takes a row and a column, because the entire thing is 5 rows and 4 columns, and it converts that those two numbers into a single number, and we are calling that state. Why we are calling it state will become clear a little bit later, because that is sort of the standard terminology. But if you just think about that, the ball can be in any of the 20 different cells, so we want to represent the position with a single integer between 0 and 19. And that is what this method will do, and this is already implemented because it's a helper, a small method. And then there is a method that sort of does the opposite, which takes a state. This will be an integer between 0 and 19, and it then converts that into a row and column pair. So it will tell you which row, which column it is, right? What do we need to implement right here is this method, deserialize. Why is it being called deserialized? Because if you think about it, in the starting you have like uh, a string based description of the game, right? This is the starting stage in terms of the string. You can write this to a file, you can read it back. That is the nice thing. So you can think of it as a serialized version that can be written to an array, or it can be written out to disk, and then that can be read back. And what we want to do is we want to read in this description and then represent it in terms of a data structure where we can move things around more easily. You can do that by using the exact data structures that you have right here, but for reasons that will become clear, we want to make a few changes. We want to represent things a little differently. So what deserialize does is it will take a map. A map will be a list of list, like this one. You can pass arena as the map variable, and it takes agent. Now, agent is a single string that represents your agent. So you can pass this variable as agent whenever you call deserialize. And it takes again two more strings representing the opponent and the goal, which are all already defined there, right? And what we want to do is the first thing is we want to create a numpy array. It will be a 2D array with the same number of rows and columns as there are in map. And then we want to store all of these things internally. Like I said, because we have this bit of information, but we want it to store in a class so we can keep track of it over time. And then we have all the associated methods inside the class. So we build an entire game out of this description, right? So there are to-dos inside this class. There are bits of code that have to be written. We have to figure out how many rows there are. So once you get that list of list, uh, obviously we sort of know that there are 5 rows, 4 columns, but I don't want that hard coded, because what we eventually want to do is to be able to change this description. So I should be able to add more rows, more columns, more players, different positions, and that should automatically get converted into a class like this. So please don't hard code anything, but we want the number of rows, the number of columns, the number of states, which will just be the product of the rows and the columns. uh, of course, we want to store the map itself, which is the list of list, the description. Uh, we want to capture the string that is representing the agent, the opponent, and the goal. These are directly coming as parameters to this function, so you can just store them. Then there is something that we are doing over here. So we are defining 3 new variables. One is the initial state, one is goal state, and one is opponent state, right? So these are sort of scalar scalar variables. They are set to none, but this one is a list. And what we want to do is, because I said the description can change, So tomorrow I want to have a description where the player maybe starts somewhere in the middle instead of the top left, or there are additional defenders or whatever changes, right? So we are not assuming that these things are fixed. So what we want to change is we want to scan the entire description. So there are two for loops, this one and then this one, nested for loops that go over the rows and columns of this description, and they look for specific things. So either a position will have the ball, or the position will have a goalpost, or it will be all empty, or it will have a defender. And there are different actions that we want to take in those cases, right? So this if condition over here, the description is over here, but if you find an agent, if you see that position has the ball, the string representing the ball present there, then you want to capture that position. And by position I mean, because we're calling it initial state, I want a single integer representing where the ball is on the field. I want that to be captured here. And after I do that, I sort of erase that ball from the description, right? Because if you look at what map is, so we are setting map right here, but map is just supposed to be a 2D representation and numpy array of the description that you're passing, right? So this will include the ball and the defenders and everything. So I'm erasing this. Why am I doing this? Because sort of want to decouple the player and the field, because if you remove the player, then the rest of the field is static. So I want to just store the rest of the field in this map variable, and I want to store the position of the player in this variable. So they get decoupled, and then whenever I want to print both, I will just combine these two pieces of information again. This is what you do in this if condition. If you are scanning and you find an opponent, then you just add its position again. By position I mean state, a single integer. So you add that to this list, which is initially empty. So keep adding all the opponents and their positions to this list. And if you eventually reach the bottom right, or wherever the goal state is, so again, not making any assumptions, so wherever the goal state is, when you reach that position, then again just store that in this goal state variable. This is all we have to do. Then at the bottom there are some assertions which are just to make sure that once we have implemented these things, we have implemented them correctly. So it is just checking that none of these variables is empty. So you have set it to something. Obviously, it's not a very robust test case, but there's a little bit of sanity check that should be present. So this is sort of what we have to do in this second step, right? And once we fill in this code, once we are sure that this is correct syntactically, then we can just try to run the next cell. Uh, if you are already familiar with Python, so we don't have the init function right now. We don't have the constructor, so the default constructor will be used. We shouldn't worry about that. The whole point of running this cell is to make sure that there are no evident syntax error at this point, right? So this is what we want to do. Now there's very little time left into this session, but we still want to give it a try. So let's go to breakout room once again, and at least try to write whatever code we can write today, and then tomorrow we can write a little bit more, and then next week we can go through all the steps up to step 12. And once we have the entire thing ready, then we go down all the way down. And this isn't a lot of work. There's a lot of repetition because I wanted to keep it a very step-by-step thing. So if you go here, so step 8 is where the implementation ends, and then step 9 you just do a sanity check by trying to create that environment. And then step 10 is interesting. Here is where you want to sort of play the game, sort of interact with the game the way we did with the car driving example. So this is not a lot of work, but being able to understand the specifications and then map it to the code, that will take some time. So let's try to do it. I'll create breakout rooms. Yes, I just launched, I think 5 different breakout rooms. Yep. So you'll be randomly assigned to one of the breakout rooms. You'll see a pop-up, select yes, go to the breakout room, try to implement the code, and obviously try to talk to other members in the room. Yeah, this room has a very low attendance. People didn't join or did they drop out?
I guess people dropped out. I don't know how many people. I'm feeling. Did everybody drop out or something? Are there?
Okay, I think either I'm not audible or it seems
You
to
are
be
audible. Are you audible? I mean, am I audible? Hello. Hello.
Sorry, I was on mute. So I was saying I know we are already over time. So I have started the process to shut down the rooms. It will take a minute and I'll let everyone join. And then we'll briefly discuss what is expected of writing this code. And then we can wrap up for today.
Yeah, sorry, we were discussing something that is a doubt in the code. So there is a map and there is an arena. So map and arena are synonymous. Is that somewhere we have to just equate them, or what is that?
Yeah, so we have given it the name arena, the variable we have defined outside the class. That variable has to be passed to the parameter map.
So that will be a self dot map. That's what we are trying to create.
Right, that will map to self dot.
But then in the template code where there is a comparison for map without the self dot, it's just a map that's supposed to be arena.
Could you tell me which line number it is?
This is the when you're defining the class of Foolsball,
right?
That is for where you are building the map. Right? When you're trying to build the self dot map. So the conditions, if map of row column is equal to an age, and I can't find a right line number here.
Oh, right.
Supposed to be arena itself.
Right here, right? Can you look at my screen? Is it line number 40?
I can see something else on your screen. So are you in the part of the?
Wait a second. I'll try to. share again.
Yes,
Can you
that's
see
the
it? Right? Yeah. So the reason is because we haven't updated self.map. Actually, we have. Yes. So yeah, at this point, you have access to both map and self.map. So you could use either of the variables.
But
This
map
information.
itself is not defined. No, there is an arena defined at the top.
No, map comes from here, right? This parameter is map, right?
Oh, I see. Okay, okay. You are
Right.
going to
So yeah, so when we call this function, then you can pass the arena variable uh, to corresponding to this parameter.
just that the name got changed from
Yeah.
arena to map. Yeah.
Yeah. I think it would be a little confusing if I called this variable over here map as well, then the parameter is map. I mean, it's totally a legal thing to do with Python, but it gets a little confusing. So
Yeah,
okay,
I will
so
have to drop off because I have another
right.
meeting. Yeah,
Sure.
thank you.
No issues. Thank you. Uh, I understand that we are over time. I don't want to hold anyone back. Very quickly, the idea, and I mentioned this in the breakout rooms, is that everyone finishes the implementation. So as many steps as you can whenever you get time, and then we will continue from step 2 onwards in our office hours whenever we decide to do that next week. uh, the solution is there in this notebook itself. So if you look at step 2, you have to implement deserialize method. But if you go to step 3, that deserialize method is already implemented. Right now, there could be many different ways of doing the same thing. So I don't expect you to use the code that I have given. That is okay, right? Write your own code, use that code, but just make sure that roughly things are tallying up and you are setting the variables correctly. Of course, we'll find that by the end when everything is implemented in step 8 and 9. When you run, then the behavior should be the same that I'm getting. Uh, but the solutions are all there because this is not a coding exercise at all. Uh, the idea is to understand how we are implementing things and why we are implementing things the way we are implementing them, because then we are going to build on top of this, add more complexity, and we are going to interact with this environment, and we're going to write algorithms to change things and basically learn to play the game. So we will have to spend some time. It's not a lot of implementation, but because the API is sort of defined by me, so you have to understand how things are connected, which functions call which other functions, and those things. Right. So we will do that. We will go through it step by step in Monday's session. Right now, if you want to drop off, that's totally okay. We are over time. If you want to stay back, if there's any questions, I'm happy to answer those questions. Otherwise, we wrap up the session for today. Then my only request is that you go back to Slack and select your preferred slot for the office hours, so that we decide that by end of the day, and then next week we have those office hours where we sort of go through the solution. And of course, once we have this ready, then we start talking about the actual problem and our approach to solving the problem. So are there any questions? I think this one in the chat. Okay. No, there are no questions, but if there are questions, let me know quickly.
Thanks, Farhan. See you next week.
Sure. Thank you. See you.
Just some questions I have about that Slack. Whether I just want to make sure I'm in all the groups correctly.
Okay. Okay. I'll ensure that I will add everyone to both the channel, general channel and the private channel by tonight.
Okay. So here in the collab, I'm using the collab also for the first time. When it says copy of this rediscovering dot whole thing and it shows the Google Drive icon, it means that it's the copy on my drive, right? That's what it means.
Yeah, it is being saved to your drive.
So if I make a change, my personal copy that's getting changed.
Right.
Because once I've done the save a copy in drive, basically it doesn't all the changes going to that. That's what it means.
Right. Right.
All right.
Cool.
Okay, thanks.
Cool. Thank you so much for attending the session. I'll see you next week. Thanks. Bye-bye.